Section 3 of Chapter 7. In this section, you're going to be introduced to logarithms and logarithmic functions. This is the first of two sections where we're going to be talking specifically about logarithms and really just being introduced to them. Tomorrow, you'll be looking at properties of logs. So, what is a logarithm? That's a very good question. That's what we're going to be looking at today. First of all, learning targets. I can write equivalent forms for exponential and logarithmic functions. This is a lot easier than it sounds and is one of the main things you're going to be doing today. I can write, evaluate, and graph logarithmic functions. The writing is a little bit, there's some evaluation, a couple graphing problems. Not too much there, but graphing is really just make a table and laser pointer. It's just make a table and then plot the points. So let's look at logarithmic equations. The first question is, what is a logarithm? A logarithm is a way of writing an exponential function that gets the exponent or gets the variable out of the exponent, so you can actually do something with it. We'll talk a little bit later about some of the applications of logarithms, but really it's just a way of getting the variable out of an exponent. It's a function that talks about the magnitude of a function. So the definition of a logarithm, or in equation form, we're going to look at exponential equations like b to the x equals a, and logarithmic equations, which looks like log base b of a equals x. I know when I actually write this, there are very few things I write in cursive. Log is one of them. So if you see my writing of it and there's cursive, it's probably just log. So we have these two equations, exponential and logarithmic, and we're using the same letters. And these are the same. The b and this b are the same thing. In fact, this is the base, and this is the log of the base. When we say this, it's log base b. The a, what it's equal to, b to the x equals a, goes inside the log. It's right here. And then the exponent ends up being what it's equal to over here. I know when I was learning about it, the phrase that I still remember is the log is the exponent. When we look at that as changing that into an equation, the log is means equals the exponent. The x is over here. And so when we look at a logarithmic equation, this really says b to this power equals a, which is what it looks like in the exponential equation. And we're going to be going back and forth between these two today. This is that first learning target where you can express it both ways. All we're doing is rearranging the values. So let's look at some of these. Let's write exponential equations as logarithms. So we have 4 to the 1.5 equals 8. Well, the 4 is the b, so it's going to be log base 4. The 1.5 is the x, so it'll be equal to 1.5. And the 8 is the a, so that's what will go inside the log. So it'll be log base 4 of 8 equals 1.5. All we did was rearrange the things that we had and put them into a log. So let's look at another one. 10 to the negative 2 equals 0.01. We're going to rearrange these, write it as a log. See if you can do it really quick. I'm not going to pause it. There's no work here. So as I'm speaking, do you think you have it? Well, the 10 is the base, so that'll go where the 4 is. The negative 2 is the exponent. That'll go over here. And the 0.01 will go right there. So we have log base 10 of 0.01 equals negative 2. The pieces just got rearranged exactly like they did up here. As we're talking about this log base 10, I'm going to throw another vocab word at you, and that's going to be the common logarithm, or just the common log. And all that is log base 10. We don't actually have to write the 10. If you have log base 10 of a, it equals log a. It's log base 10 is used a lot, so it's just shorthand. It's not wrong to have the 10. We just don't usually write it, just like we don't usually write 1x to the first power plus 0. It's just x. Same idea. The common log is used a lot, and specifically many years ago it was because we would figure out logs by using tables. Well, we'd have tables of common logs, and we'd have to use formulas to make it into the common log. Recently, we'll find a lot of logs using our calculator. Your calculators, up until just recently, could do exactly 2 logs, one of which is the common log. You have a log button on your calculator, whether it's scientific or graphing, that would be log base 10. Yes, there are ways to get to the other bases, but we don't actually really need to know how to do that. So that log button is log base 10. We'll learn about the other log that it does in the second half of the chapter. So this log base 10 of 0.01 equals negative 2, we could write simply as log of 0.01 equals negative 2. It means the same thing. They are both right. The biggest important piece is if it gives it to you like this, you have to recognize that's log base 10. And we'll be working with that some more. So that would be taking exponential, writing as a logarithm. We can also go the other way. Get a log, write it as an exponential equation. So we'd have log base x of negative 16 equals 3. Well, log base x, so the b, that's going to be the base over here. We're going to have x to a power. The 3 is the exponent, so x to the third equals negative 16. And that would be it. Try this one real quick. Log base 6 of x equals 3. Write it using an exponent. Do you have it yet? Do you have it yet? Do you have it yet? All right, so this says 6 to the third power equals x. 6 to the third power equals x, which you could simplify this if you really wanted to. X equals 216 because that's 6 cubed, but we just need to write it using an exponent here. The other thing we're going to be doing is simplifying or evaluating, and this is using mental math. These are all going to come out nice. They're going to be fairly small numbers, things like that, but it's going to be things like log base 7 of 343 equals something. Now, when you think about this, think about it as an exponential equation. 7 to some power equals 343. 7 to what power? Well, we know 7 to the first equals 7. 7 squared is 49. Times another 7 is 343. So that would be 7 cubed equals 343. So the log base 7 of 343 equals 3 because it was 7 cubed. Same deal. Log base 3 of 1/9 equals something. So 3 to the what power equals 1/9. You might be thinking, holy cow, a fraction. Don't pay attention to the fraction right now. What's the important part of this fraction? The 9. 3 to the what power equals 9? If you said 3, no. 2. 3 to the second equals 9. Well, how do we get it flipped into the denominator? Negative exponent. So 3 to the second equals 9. 3 to the negative 2 equals 1 over 9. So this was part of that second piece of learning target. We'll also look at some functions here. But this is just using mental math. They'll all come out nice. We won't have to worry about 7 to the 2.53 equaling something. We'll be dealing with that in the second half of the chapter. But right now, you're just thinking, all right, 3 to the what equals 1/9. Work your way through it, -2. So before we move on, while we still have all these notes on this page, let's try a couple. So right as a logarithm, we have x to the 2.5 equals 32. 6 to the x equals 216. Right as an exponent, log base 5 of 625 equals 4. And simplify, log base 4 of 64. So go ahead, pause this for a minute. None of these should take very long because there's no actual work to do to speak of. But go ahead and see what you can get with these and push play when you're done. All right, how were they? Were they good? Were they easy? Do you think you have them? So let's look at the first one. Right as a log. We're going to have log the base x of 32 equals our exponent of 2.5. Is that what you got? It's just rearranging the stuff. 6 to the x equals 216. 6 is the base, equals x. So we have log base 6 of 216 equals x. Interestingly enough, did you notice that this problem and this problem were actually the same? Because 6 cubed equals 216. So that would be cubed. Yep. Right as an exponent. We have log base 5 of 625 equals 4. That means 5 to the 4th power equals 625. If you had gotten that in a different direction, like 4 to the 5th power, doesn't equal 625. 4 to the 625, 5 to the 625, doesn't equal 4 or 5. This is really the only way that actually even makes sense here. And then log base 4 of 64, 4 to the what power equals 64? If you thought 3, then yes, that is right. So this is most of what we're doing today. There's a little bit more we're going to talk about, but this is the bulk of it. Kind of weird, but there's no real math that we're doing for the most part. So that'll be most of it, but let's look at that extra little bit too. We have some special properties, and apparently 0 showing up out of the blue is a special property as well. So we have 2 special properties. Most of the properties we're going to look at next time, but the 2 we're going to look at, log base b of b is going to equal something. Well, this is saying b to some power equals b. Well, something to the what power is going to equal itself? Something to the first power equals itself. So if these 2 things are the same, it's going to equal 1. The other one, b to the what power equals 1, well, this 0's been here, so we know that b, anything to the 0 power equals 1. Those are the 2 special properties we're going to see today. You'll have a couple questions on that, but it basically just plugs in a number for b. It does not matter what the number is. This will still be true. The next piece is an application. pH. This would be like the pH balance of something. You'll talk about pH balance of water, pH balance of lemon juice, orange juice, the whole acid and base thing. It's a chemistry thing you'll be learning about. pH is just the proportion of hydrogen ions in something. There's a very small equation to find that. The pH equals the negative log of the concentration of hydrogen ions. And this looks kind of complicated because we have like the square bracket, we have H and plus in the exponent. That's just the hydrogen ions as opposed to hydrogen atoms. Basically what the problem's going to do is it's going to give you a number like 0.0000537. You take the log of it in your calculator, it'll give you a number like -2. You slap it with this negative to make it a positive. That's how all of these work. So, an example, What is the pH of iced tea with a hydrogen ion concentration of 0.000158 moles per liter? Here's that number. We're just going to take the log of this in our calculator. So we plug it in, take the log of it in our calculator to get negative 3.8 something something something. Well, this negative makes this positive, and the pH equals 3.8. There's really nothing more to that. The question might ask a follow-up question like, is it in this range? Like, is this going to be in between 4 and 5.5? No, 3.8 is not in between 4 and 5.5. So the follow-up question is generally a pretty easy one. Logs have a lot of other property or a lot of other applications as well. They're used in a lot of scales. We'll be talking about these a bit throughout the chapter, but the luminosity scale, which measures the brightness of stars, is a logarithmic scale. The Richter scale that measures the power of earthquakes is logarithmic. The decibel scale that measures the loudness of sound is a logarithmic scale. And logarithms have been used to do things like crazy things like cancel out sound. When I think it was Mercedes was the first car that really had good sound cancellations, they ran microphones under their cars to get road noise, and then they used logs to end up canceling out that noise, so that it was a quieter ride. Anyway, that's just some applications of logs that we'll be looking at a little bit throughout the chapter. Now let's go to inverse of an exponential function. Last time we were talking about inverses, and so we just jumped into logs. So let's look how this actually connects. If we start out with an exponential function, just y equals 2 to the x, we can find the inverse. The first step would be switch x and y. So we do that. And then we need to get y equals something. Well, y is in the exponent. How would we possibly get y out of the exponent to make it equal something? We write it as a logarithm. We can rewrite this as log base 2 of x equals y. So we can see that this is the inverse of this. The log is the inverse of the exponential function. Weird how we'd be talking about them at the same time, along with inverses. And so, using this, you'll get questions like, use the given x values to graph the function, then find and graph its inverse, describe the domain and range of each, kind of like what we did on our calculator lab. And so it'll give us a function, f of x equals 5 to the x, and then x equals, it'll give us some numbers, -2, -1, 0, 1, and 2. And we're going to make a table. We have our x values, and we can just plug them in. I like to start with easy ones. 5 to the first, no, that one's 5. 5 squared, 25. Anything to the 0 is 1. If we go to negatives, means we flip it over, 1/5 and 1/25. And then we can graph this. So we get an appropriately scaled graph. Chances are we're not going to be able to graph all of these on the same graph. If we were to graph, if we had a graph big enough to graph 25, we're barely going to be able to see 1, much less these guys. These would just be on the axis. In fact, this one's going to be on the axis as it is, pretty much. But we can plot our points. -2, 1/25, -1, 1/5, 0, 1, 1/5, and then 2/25 is way up here somewhere. We're just not going to graph it. But we can use these points, connect the dots, and we get our exponential function. Next, we can find the inverse. Well, we're going to find the inverse using exactly these same steps. In fact, it is exactly the same. Just replace the 2 with a 5, and you have it. So the inverse is just log base 5 of x. Well, we're not going to plug in these x values for the x because these are the x values for the function. They'd be the y values for the x. But we're not actually going to plug any values into this at all, because what do we know about inverses. You just switch the x and the y, just like we switched the x and the y here. Well, we can switch the x and the y on the table as well. Instead of doing it again, hey, this is now my x column, this is my y column. And so we can graph these points. 1/25th, comma, -2. It's going to be over 1/25th, which is nothing, and down to -2. And we get a point. Over 1/5, down 1. Over 1, down 0. Over 5, up 1. And then the 2 over 25 up 2, we're not going to get over to 25. But then we can connect the dots. So exponential functions, by the way, are the fastest growing function. It'll grow faster than anything. If we had f of x equals x to the 100 power, 5 to the x will be bigger than that pretty soon. On the other hand, logarithmic functions are the slowest growing functions. Here it took us 4 to go up 1. We're going to have to go over another 20 to get to 25 to get up to 2. We're going to have to go over another 100 to get up to 125 before we get up to 3. We're going to have to get up to 625 before we get up to 4. I mean, that is a very, very slow growing function. Let's see. Oh yeah, domain and range. Finding the domain and range. Well, the domain is what x can equal. The range is what y can equal. Start out with the function. The domain of an exponential function is all reals. We could plug any x value we want into this, and we're going to get a y value. The range isn't going to be all reals because we have this horizontal asymptote. And so the range, y is going to be greater than 0. Not greater than or equal to, because it'll never actually touch 0. It'll get really, really close. But that's it. And for the inverse, these two things just switch. The domain, x is greater than 0. We have a vertical asymptote here. It'll get really close to 0, but it will never actually touch it. And the range will be all reals, because y will be able to go anywhere it wants. And again, you have a little bit of this stuff. We'll be working more with this later on in the chapter, but there is a little bit today that's introduced. Anyway, that would be an introduction to logarithms as functions, as inverses, as what is it. Most of what you're doing is just going to be changing around some numbers. Not a whole lot of math involved in it. And we'll look at properties more next time, but just be ready to be answering a few questions in class. And don't forget to leave a comment. See you later.